Hi children, today we are going to see some other important terms in the field of current electricity apart from what we have already seen. There are so many terms we have seen. Apart from that, some other important terms we are going to see that I have already written. So what is that? First one, number one is current density. Then number two is conductance and number three is conductivity. Okay, so to start with, we will see what is current density. So now we are going to see what is current density. See, current density is actually denoted by, what is the symbol for current density is capital J. Okay, so how to define? Say current density is defined only at a point in a conductor. Okay, therefore current density at a point in a conductor is defined as the amount of current flowing per unit area of the conductor, okay, taken around that point, provided that area is held normal to the flow of current. Okay, once again, see what is current density. Current density at a point in a conductor is defined as the amount of current flowing per unit area of the conductor, okay, taken around that point, provided the area is held normal to the direction of current. Okay, therefore area is held normal to the direction of the area only. Area is normal to the flow of current means, I think you have idea about area vector. Therefore area vector should be parallel to the direction of current. Are you following? I think you know if area and area vector, if there is some area is here, see this is okay, therefore what is that? Area vector means what is the direction of area? This is area vector means what is that? This will be the direction of area vector, normal. Okay, outward normal is area vector, already we have seen. Okay, right. Therefore now what is that? Once again I am repeating the definition. Okay, so what is that? Current density at a point in a conductor is defined as amount of current flowing per unit area of the conductor taken around that point, provided the area is held normal to the flow of current. Okay, therefore now let me explain this in detail. See, for example, I have, okay, one area. See, this is the, okay, area. Okay, now this is what is the area vector direction. Area vector direction will be, this is your area vector, correct? Okay, now what is the direction of the current? Let me say that the direction of the current is, okay, let it be, see, this is the direction of current. This is the direction of current. This is the current. Okay, therefore you can say I and, see what is that? Your area is held normal to the current. Therefore area vector will be, what is that? Parallel to the direction of the current. Are you following? I and A vector are both are in the same direction, which means that area is held normal to the flow of current. Correct? I think, hope you are following. Okay, therefore you can say this is what is your, now I have to give what is current density. Therefore current density J, current density J here, that is nothing but, what is that? Amount of current flowing per unit area, correct? Therefore current divided by unit area, current by unit area. So this is what is that? The expression for current density, provided what is the area is held normal to the current. But there are cases if the area is not exactly normal. See, for example, see, this is, okay, now what we have taken, right? Here, but now we'll slightly I am tilting the area. Therefore, tilting means, see, okay, let me have this one as the dotted line so that it will be easy for you. See, this is the previous area what we have taken. Okay. Now, what I am doing is, I am slightly tilting the, what is that, the area of the conductor, the area of cross section. Therefore, now, what is that? I am slightly tilting like this. Are you following? Okay, therefore, now you tell me what should be the area vector. Area vector, definitely it will be change difference. Okay, therefore the area vector of course, this is normal to the area and always. Therefore, this will be the area vector. This will be the area vector. But the current direction is same. What is the direction of the current? Current direction is like this. Current direction is like this. Okay, hope you are following, children. Okay, so therefore, now what is the angle between, current and the area vector? This is, okay, therefore let it be theta. Okay, therefore, what is the component of area here? See, because very important is the area should be held normal to the current, normal to the current. Therefore, which is here, only component of area vector is only normal here. Which is normal here? In this direction, A cos theta will be in this direction. Correct? A cos theta will be in this direction. Therefore, in this case, if I have to write for this, okay, if I have to write current density, therefore for that, current density, okay, J, that is equal to I by A cos theta. In this case, both are, area is held normal, therefore area vector and I are in the same direction. But here tilted, therefore area is not normal. Actually the area is not held normal to the current. Therefore, which component of area vector is normal? A cos theta. Therefore, J, that is equal to I by A cos theta. Therefore, you can say from this, what is your I? Therefore, J A cos theta. Correct? Therefore, you can say I, that is equal to J dot A. Once again, I just want to tell you, area, current is a scalar, current density is a vector. Because why? It is, what is that? Current per unit area held normal to the current. Therefore, here we are considering that area vector here. Therefore, here, what is that? Current density is a vector, but current is a scalar, which means that we can make it, I is nothing but, okay, the scalar product, dot product of J and A, current density and the area vector. Okay, right. Therefore, what is a unit of J? Unit of J is nothing but, what is that? Ampere per meter square. Ampere per meter square. Therefore, what is the dimension? Dimension of J. That is nothing but ampere. A, I. Okay. And what is that? Meter square, L squared. Meter squared, na? A, L squared. Are you following? So, this is about current density. Current density is I by A. Right. Now, this is number 1. First, this is number 1. Okay. First one. Okay. Number 2. What is the number 2 is conductance, na? Therefore, what is conductance? Very simple. What is conductance? Conductance is usually, it is denoted by G. What is the symbol? G. Capital G. Okay. Therefore, what is conductance? Very simple. It is nothing but reciprocal of resistance is conductance. Reciprocal of resistance is conductance. Therefore, what is G? Reciprocal of resistance is conductance for 1 by R. That's all. Very simple. Okay. Therefore, the conductance of a conductor is nothing but reciprocal of the resistance. Okay, therefore, what is the unit? Unit of G is nothing but, what is the ohm inverse na? Ohm inverse. That is nothing but, it is reciprocal of resistance, so therefore you just inverse of resistance. Okay, therefore here it is nothing but mho. It is also called as mho, just reverse, mho. Okay, or it is what is called Siemen, S-I-M-E-N, that is capital S. So this is about what is called a conductance. Okay, conductance is nothing but the reciprocal of resistance. Okay, right. I think dimension you can, because resistance you know, dimension you can write. Okay, there is no need for me to write. Okay, now next one, third one. Third one is what is called conductivity. Everything is electrical conductance, electrical conductance. There is no need to tell every time because we are dealing with what is that? Current electricity. Therefore, what is electrical conductivity? Conductivity means it is electrical conductivity. Okay, okay, because we have seen heat also na last year. This we are dealing now with current electricity. Conductivity. Conductivity is denoted by sigma. Okay, what is conductivity? Conductivity is nothing but reciprocal of resistivity. Conductivity is nothing but reciprocal of resistivity. Therefore, what is unit of sigma? That is nothing but rho. Rho unit is, what is that? Ohm meter na? Ohm meter. Therefore, here unit. Okay, therefore unit of sigma here is nothing but 1 by rho, means it is ohm inverse and meter inverse, correct? Okay, therefore it can be also a mho, na? I told you this is MO, MHO, mho, meter inverse. Okay, mho is also what is called, or it is Siemen, and okay, therefore it is yes, m power minus 1. Okay, therefore this is I think what is the dimension of electrical conductor? I think you can do, no, there is no problem. Okay, you have to derive, because already we have seen what is for resistivity. From that, inverse of that, it gives you what is called conductivity. Okay, now what is the formula for see? I think already we have seen what is rho. Rho is nothing but, what is formula for rho is m by n is quite tau, no? In the previous class we have seen. Okay, therefore, which means that what is sigma? Therefore, sigma, that is equal to 1 by rho. That is equal to n is quite tau by m. N is quite tau by m. Are you following? Therefore, you can even say that here on what factors it depends. It depends. Therefore, as resistivity, it depends on the nature of the conductor as well as what is that temperature, tau. Okay. Therefore, here sigma here conductance. Okay. Conductance sigma is what is a proportional to the relaxation time. What is relaxation time? Time interval between two successive collision. Okay, therefore, and that is tau depends very much on temperature. More the temperature, less will be tau. Less will be tau. Are you following? More the temperature, less will be. Therefore, tau is inversely proportional to temperature. Correct? More the temperature, less will be tau, because more number will be the number of collision. I think everything we have seen in our previous class. Okay, therefore if you have any doubt, go through that once again. Okay, therefore tau is inversely proportional to temperature. More the temperature, more is the collision. More the collision, time interval between the two successive collision will be decreased. It will be less. Okay, right. Therefore you can say sigma is inversely proportional to temperature now. Okay, therefore if you are asked to plot a graph, these are all very okay. It's very simple thing. Say sigma and t, therefore it is inversely proportional. I think you know inversely proportional graph na. Therefore, what is that? It is sigma It is T temperature. Therefore, it is inversely proportional. Therefore, it will be, let me have some other color. Okay. So, I want this. Okay. Therefore, this is how we have to plot a graph between sigma and T because they are inversely proportional. Fine. Okay. Now, shall we go to the next one? See. Next talk. Well, now we are going to see, very important. See, we have seen three. What is that? Terms here. Okay. Now, what is it really? How are they related between? What are related? Okay. How? For example, now the relation between. Now, I just want to give you relation between. Let me have this. Relation between J. What is J? Current density. Okay. And sigma conductance and E. Very, very important. It has a lot of significance. Maybe I will tell you later. Okay. Sigma, J, sigma and E. Okay. So what is that? Let us go for any other color, green. Right. So now we know that how conductance, current density and electric field intensity all are related. For that, I think you have idea about the relation between current and drift velocity. Correct? Current is equal to NEAVD. Okay. Right. Therefore, what is current density here? Current density J, that is equal to I by A, na? I by A, that is equal to NEVD. But I want the relation between current density, conductance and E. Okay. Therefore, how can I? That is nothing but VD. I want to represent in terms of VD in terms of E. Okay. Therefore, how are they related? N, E. Okay. N, E. And what is VD? VD is E by M na? Into tau. Already we have seen. Are you following? Therefore, you can say that, therefore, what is J? J is equal to N E squared tau E by M. Are you following? That is nothing but, somehow I want to bring sigma here. I want to bring. Okay. Therefore, you can say it is also, if you want. Okay. I'll write in terms of E by, that is nothing but E divided by M by N E squared tau. M by N E squared tau mane kya hota? What is this? Is this nothing but rho, resistivity. Therefore, okay, that is nothing but E by rho. E by rho. And rho, 1 by rho is nothing but sigma. Okay, therefore it can be 1 by rho is sigma, means it can become sigma E. Are you following? So you got the relation. What is that? J. Therefore, how J sigma J, that is equal to sigma E. J is equal to sigma E. Following? Okay, right. Next one. See, but this, as I told you, this expression is very, very, very important. Why? Okay, that we will see now. What is that? See, here, very important. J, what is J? Once again, I by A. J is I by A. Okay, that is equal to, okay, what is sigma? Okay, sigma into what is E in terms of potential difference, V by L, where L is the length of the conductor. Are you following? And that is nothing but, okay, V by L into 1 sigma in terms of resistivity, 1 by rho. 1 by rho. Are you following? Okay, therefore from this you bring, therefore, very important, you see children. So what is V by, therefore V by I. V by I, that is equal to rho into L by A. R आएंगी नहीं? Okay, इधर से. See, I by A is equal to V by L into rho ना. Therefore, V by I, that is equal to rho into L by A. Okay, that is nothing but your resistance. Okay, V by I is equal to R. आपका R है ना अभी? So, we have started from J is equal to sigma E. J is equal to sigma E. Therefore, also J is I by A. Sigma E is equal to V by L. Therefore, from that you are bringing it to Ohm's law, correct? Therefore, V by I, that is equal to rho into L by A. Rho into L by A is nothing but R, which means that, okay, you have J is equal to sigma E. Okay, J is equal to sigma E is very much similar to what is that? Your Ohm's law. That is why J, that is it. Are you following? Okay, J is equal to sigma E. From that you are bringing V by I is equal to R. Okay, therefore that is, you have arrived at Ohm's law. Therefore J is equal to sigma E. Therefore J is equal to sigma E is nothing but the other form of Ohm's law. What is that? It is called the microscopic form of क्या है? Ohm's law. It's nothing but Ohm's law. Okay, or you can even, is it clear? If you want to represent in vector notation, so J, that is equal to sigma E. It is a, okay, therefore you can say it is a vector form of Ohm's law. Hope you are following, right? Right. Next one. What does he? Next relation. So we have derived the relation between what? J, sigma and E. So one more relation we will see. What is the next one is? Okay, the relation between these are all very common, children. This will come for 2 marks, 3 marks. Okay, very important even for numericals. Okay, so relation, this numericals, all these formulas you have to keep everything in tips. Okay, relation between electrical resistivity and electron mobility. Simple. Okay, electrical resistivity and electron mobility. Okay, how to? See, you know that electrical resistivity and electron mobility. Okay, so I think once again you go to I is equal to NEAVD. Okay, right? And therefore you know that J, that is equal to I by A, that is equal to NEVD. But I want to somehow bring electron mobility here, mobility. Therefore, you know mobility is nothing but, what is the ratio between drift velocity and drift velocity per unit electric field? No, it is ratio between drift velocity and electric field intensity, right? Therefore, I think instead NE into mu into E, mobility, mu into, are you following? Therefore, J, that is equal to, okay, NE mu into E, right? Also, we already have derived what is the relation between J, also J, also J, that is equal to, you know that is nothing but sigma E, na? Just now we have derived. Okay, that is nothing but sigma by rho. Why? Because I want him in terms of resistivity. So is E by rho, na? Oh, it is, sorry, it is nothing but E by rho. Why? Because I want to bring in the form of resistivity. Okay, right? Therefore, this is 1 and this is 2. Okay, both are same, both are current densities only, na? Okay, therefore you can see, therefore NE mu E equating 1 and 2, that is equal to E by sigma, E by rho. E will get cancelled. Therefore, you will be getting rho that is equal to, okay, 1 divided by N E mu. Rho is equal to 1 divided by N E mu. So this is the relation between resistivity and what is that? Mobility, electron mobility. Therefore, therefore, what is that? Rho is equal to this. Therefore, that implies sigma is equal to N E mu, no? Sigma is equal to N E mu. 1 by rho is nothing but, what is that? Sigma. 1 by rho is sigma. Therefore, you can say sigma is equal to N E mu. Is it clear? Right. So, this is about these three factors, important factors we have seen. Now, let us go to the next important topic. See, this is already we have seen. This is the effect of temperature on resistance. Already we have seen. But I want to introduce one more term, new term here. That is fine. Okay. So, what is that? Effect of temperature on resistance. Okay. Effect of temperature on resistance. On resistance. Okay. Now, for see, already we have seen for a conductor, for a metallic conductor, for a conductor, all we so far for a conductor, what is the resistance of a conductor? We have this expression is only for conductor, not for insulator, and this one R is equal to what is that? M by N E squared tau, that is rho, ML by A na, rho into L by A, correct? Therefore, this is the expression. Okay, that gives you an idea that how it depends upon the resistance of the conductor. Therefore, resistance of the conductor for a conductor R is inversely proportional to rho. R for a conductor, very important, for a conductor R is inversely proportional to rho. Rho is a relaxation time. Okay, and you know very well this many times I told you, but this tau is inversely proportional to temperature, correct? More the temperature, more will be the collision, therefore less will be the time interval between collision. Therefore, yeah, R is proportional to T for conductors, correct? For conductors. Okay, therefore, now you see. Therefore, what I am going to do here is, see, consider my conductor, okay, let RT be the resistance of the conductor, at T degrees Celsius. Okay. Therefore, let and or not be the resistance of the conductor at 0 degrees Celsius. At 0 degree Celsius. Okay. Therefore, okay, how are they related? Now we are going to see resistance, you know, varies with temperature. We know for conductor R is directly proportional to T. But what is the relation? I have idea RT is the resistance at T degree Celsius and R0 is the resistance of the conductor at 0 degree Celsius. Okay. And therefore, how are they related? RT and R0 are related. So, therefore, RT that is equal to R0 into 1 plus alpha T plus beta T squared. Okay, RT that is equal to R0 into 1 plus alpha T plus beta T squared, where alpha and beta are constants. Okay, and these constants differ from one metal to another metal, one conductor to metal, alpha and beta changes. Okay, it varies. Right, one more very important thing is, if the temperature T is not sufficiently large, very important, not sufficient, it is not small, it is not sufficiently large, okay, then, okay, now the equation, this equation, let it be 1. The equation 1 will be reduced. Now it can be reduced to RT, that is equal to R naught into 1 plus alpha T only. Alpha T only. Why? Because if the temperature is not sufficiently large, beta value can be neglected. The third term can be neglected. Therefore, you can say that 1 plus alpha T. This is only when the temperature is, what is that? Not sufficiently large. If a very high temperature means beta cannot be neglected. Okay. Therefore, now you can say, therefore, you can say RT, that is equal to R naught plus R naught into alpha T, na? Very good. Therefore, I want here, what is here? Alpha. So, here alpha, that is equal to, okay, RT minus R naught divided by R naught into T. Anna? Okay, it's very important relation, children. Okay, this is RT minus R naught into R naught into divided by R naught into T. Okay, that is nothing but, okay, you can even say this one alpha, that is alpha is equal to RT minus R. Now you know very well for conductor, you know that for conductor as, what is that? Where T here, T degree Celsius and it is 0 degree Celsius, na? Therefore, definitely, what is that? Your RT has to be larger if your T degree Celsius and 0 degree Celsius. Okay. Therefore, definitely, you can say that what is T is T degree Celsius is more than 0 degree Celsius. Therefore, you can show RT has to be more than R naught. As you increase the temperature, what is that? The resistance will increase. Therefore, RT minus R naught is, therefore, you can say increase in resistance. If you increase the temperature, resistance will increase. Therefore, you can RT minus R naught can be written as increase in resistance. Increase in resistance. Okay. Divided by original resistance. Original resistance into, what is the rise of temperature na T? From 0 it has gone to T. Therefore, it is rise of temperature. Okay. Therefore, now I can write how to define. Now here, what now? Okay, alpha, I told you. What is alpha? Alpha is a constant. It is a constant, I told you. What is that name? Name of that constant here. Alpha is called as, okay, temperature coefficient of resistance. Okay, that I have not told. Temperature coefficient of resistance. Temperature coefficient of resistance. Okay, alpha is called as temperature coefficient of resistance. How to define? Temperature coefficient of resistance is defined as, okay, increase in temperature, increase in resistance per original resistance per degree rise of temperature. Okay, temperature coefficient of resistance, okay, is defined as the increase in resistance per original resistance per degree rise of temperature. Okay, what is the unit therefore? Unit of alpha is resistance per degree, na? Therefore, you can say per Kelvin SI unit, or it is per degree Celsius. Per degree Celsius. Okay. Right. If I take, see, I have taken R naught. If I have two temperatures, for example, no, two temperatures. If for example, if at you can say at T1 degree Celsius, the same alpha I am going to give in other form. For example, I have taken at a 0 degree, another one at T. Now I am going to take two both at different temperatures, not at 0 degree Celsius. Okay, something more than 0 degree. Therefore, let at T1 degree Celsius, okay, let the resistance, or let it be R1. Resistance of the conductor is R1. Now we are dealing with conductor only so far, right? Resistance of the conductor is R1. And at T2 degree Celsius, resistance be R2. Okay. So I am orally telling everything. T1 degree Celsius, resistance is R1. Okay. T2 degree Celsius, resistance is R2. Okay. Therefore, how are they related? Okay. Therefore, you can say that alpha. Therefore, alpha can be written as increase in resistance. Therefore, in this case, how to the alpha, that is equal to increase in resistance. Therefore, here, what is that? T2 is more than T1. Therefore, R2 will be more than R1, because as you increase it for conductor. Okay, everything we are dealing now only with conductor. Therefore, as you increase the temperature, distance will also increase, right? Therefore, how to write alpha? Therefore, okay, increase in resistance. What is increase in resistance? R2 minus R1 divided by original resistance. What is original resistance? R1. Original resistance, because you have taken two resistance at T1 degree, R1. After that, I am increasing the temperature from T1 to T2. Therefore, the resistance becomes R2, right? Therefore, what is the original resistance? Per degree rise of temperature, what is the degree rise of temperature? T2 minus T1. Are you following? T2 minus T1. Here, this is with respect to 0 degrees Celsius. Here, I have taken two randomly to any temperature. Therefore, in that case, your temperature coefficient of resistance expression will be these two. That is alpha, that is equal to R2 minus R1 by original resistance R1. Degree rise of temperature is T2 minus T1. Okay, right. Now, we are going to see the values of alpha. See, what is, for example, for, you know, so far we have for conductors only we have, so for metals, any conductor, for metals, like any conductor, silver, copper, aluminium, okay, gold, whatever you say, take, for metals, you know that as you increase the temperature, okay, the resistance is increasing now. Therefore, R2 minus R1 is positive. R2 minus R1 is positive. Therefore, and what is the T2 is larger than T1. T2 is larger than T1 we have taken. Therefore, R2 minus R1 is positive. Therefore, you can say the temperature coefficient of resistance alpha is positive for, what is that? Metals. For metals. Okay, right. Now, okay, next one. For, okay, semiconductors and insulators. Okay, so I think you have idea about, let me go here. I think you have idea about semiconductors. Semiconductors, I think you have studied in your 11th standard chemistry. I know. Okay, anyhow, I'll give you a picture. See here, for semiconductors and insulators, what is alpha? Value of alpha for semiconductors and insulators. See, I can say first, I'll give the explanation afterwards. See, for semiconductors and insulators, and insulators, alpha is negative. Alpha is negative. Okay, therefore alpha means what is that? Temperature coefficient of resistance. Alpha is negative. Okay, What do you mean by that? As you increase the temperature, as because I'll write, okay, after that I'll give the explanation. Why? Because, okay, some problem. Okay, what is that? What is the reason? Reason is alpha is negative. What is the reason? Reason is because as you increase the temperature, as temperature is increased, okay, resistance is decreased. As the temperature is increased, it is temperature, capital T temperature, R is resistance. As the temperature is increased, resistance is decreased. Unlike your, what is it, conductor. For conductor, resistance increases with, what is the temperature? With the temperature. But here, okay, why? Because in the case of conductor, as you increase the temperature, number of collision will increase. Therefore, in the case of conductor, resistance is because of collision of electrons with the ions. But here, it is different. Why? Because in semiconductors and in the charge carriers in semiconductors is very, very less. Okay, and as room temperature, if you say, okay, and therefore what is and the how I think you would have studied something about the conduction band and valence band. So here in the case of semiconductor, okay, it is you have already studied, but anyhow we will be seeing in other chapters also. Last that is electronic devices. Okay, anyhow I'll give you a slight picture of what is a semiconductor and what is a insulator. Only then, if you know that, only then you can understand the concept here. So in the case of semiconductor, you see there are what is that, valence and conduction band. Okay, valence band and conduction band. This is conduction band. Conduction band, what is that? Electrons will be there. It is not new to you, I know, but anyhow. But in the case of valence band, this is a conduction band and this is the valence band. Okay, valence band, what actually is, see, what is the electrons in the conduction band, they are only responsible for conduction. How the valence band, conduction band is getting the electrons? Only, see, this is valence band is fully actually filled at 0 Kelvin. Valence band will be fully filled, filled with electrons. Conduction band is fully empty. But at the room temperature, what will happen? Some of the electrons will jump from, what is that, valence band to conduction band, thereby creating some holes here. Okay, holes. And don't bother about that. Okay, we are bothering about what is that, electrons which are in the, that we will see, everything we will see in the later chapters. Now what is required here? See, the electrons in the conduction band here, this is the electrons. Okay, these are all electrons. This what is that, dots. Okay, so these are electrons. And here, therefore, once the electrons are jumping from valence band to conduction band, thereby creating, it is what is called holes. Here, hole, there is a vacancy is created, and thereby creating vacancy, what they are jumping to conduction band. Okay, there is some gap is there between valence band and conduction band. Okay, and this is gap is Eg. Okay, and this gap is very small. Okay, it is you can even say it is less than 3 electron volt or something like that around. Okay, therefore what is that, therefore it is less, so that the electrons, what they can do, they can jump from valence band to conduction band. They can easily jump from valence band to conduction band. Why? Because even at room temperature, Even at room temperature, they are having thermal energy now. Because they are having thermal energy, they are able to overcome the energy gap, and thereby they are jumping from valence band to conduction band. So once they are going to conduction band, they are ready for conduction. Electrons only in the conduction band. Here valence band also there will be electrons. Here these electrons, lowermost electrons, they cannot overcome the energy gap, so they are staying in valence band only, but they are not for conduction. Okay, but electrons in the conduction band only, they are meant for conduction. So what happens, all these electrons in the conduction band, here there will be energy levels will be there anyhow. Okay, there will be energy levels, and so electrons in the which band, conduction band only, they are meant for conduction. That is why what happens, as the electrons are jumping from valence band to conduction band, and they are now available for conduction. Okay, and you see why here I am coming to your Eg is less than 3 electron volt. Okay, right. Therefore, even at room temperature, some of the electrons, they can manage to overcome this energy gap and they jump to conduction band. So some of the electrons are available in the conduction band, so they have some conductivity even at room temperature. At room temperature, there are some electrons found in the conduction band. But if you come to insulators, the case of insulators, what is difference between semiconductor and insulator? Means, see here, insulators conduction band is there. Okay, these are energy levels, and here is the valence band. Okay, valence band. Okay, and here the valence band has so many, filled, every level is filled with electrons. Okay, but here the gap is there, no? Here this gap is what is called Eg, the gap between the conduction band and the valence band. Here that Eg is very large, more than 3 electron volt, very large. So at room temperature, okay, even at the room temperature, the electrons in the valence band, okay, they cannot overcome this much of gap of 3 electron volt. Okay, and they cannot jump to conduction band. Therefore, at room temperature, conduction band is empty here. At room temperature, conduction band is empty. There is no electrons at all. Okay, are you following? This is at room temperature. Right. Now, let me go to the next step. If you increase the temperature, as you increase the temperature, what will happen? The more number of electrons, okay, the electrons get more energy, more thermal energy as you increase the temperature. So more number of electrons, there is a possibility of more number of electrons to jump from valence band to conduction band, correct? Okay, therefore more number of electrons will be available at conduction band, and electrons in the conduction band is only meant for conduction in the case of semiconductor and insulators. Okay, therefore at temperature more than the room temperature, after you increase the temperature, okay, therefore more and more number of electrons will be jumping from valence band to conduction band. Therefore you will be getting so many number of electrons will be available now in the conduction band. Even in the case of insulators also, because as you increase the temperature, there are some possibility for the electrons in the uppermost energy level of valence band, they may jump even to the conduction band. There may be possibility. Why? Because as you increase the temperature is extremely large, so many electrons will jump from valence band to conduction band. So what will happen? Once the conduction band is having electrons, then they are ready for conduction. Number of electrons in the conduction band is increasing as you increase the temperature. Okay, therefore as you increase the temperature, what will happen? Resistance will decrease here. As that is why I told you. That is why. Therefore, as you increase the temperature, more number of electrons will be there in the conduction band. Therefore, their conductivity will increase. Therefore, resistance definitely it will decrease. Are you following? Therefore, for semiconductor and insulators, alpha is negative. Why? Why? What is alpha? Alpha is nothing but R2 minus R1 divided by R1 into T2 minus T1. Correct? Therefore, R2 minus R1 is, what is that? Is negative. Okay, here in this case. Why? Because T2 is larger than T1. T2 larger than T1. Therefore, here R2 will be, what is that? R2 will be less than R1 in this case. Why? Because as you increase the temperature, resistance will decrease. Why? More number of electrons are available now with the conduction band for conduction. Their conductivity will increase. Therefore, resistance will decrease as you increase the temperature. Therefore, what is that? R2 minus R1 will be negative now. Therefore, alpha will be negative. So, temperature coefficient of resistance for insulators and what is that? Semiconductors is negative. Okay, is negative. Whereas for metals, temperature coefficient of resistance is positive. Okay, right. Everything, the semiconductor, insulator, everything we will see afterwards in detail in other chapters. Okay, just I have given you just to understand this because alpha is negative. How? That is why I explained here. Right. Now, next is very important one is for alloys. What is value for temperature coefficient of resistance? See, alloys means it is nothing but a mixture of metals. Okay, alloys like I'll give you. Okay, manganese. Okay, manganese, and you can say nichrome, manganese, constantan. Okay, and nichrome. What happens here is, okay, for these okay, what happens here is the alpha here is positive only because they are nothing but after all they are the mixture of what is that? They are many metals. Okay, for metals alpha is positive now. But what is the difference between metal and alloy here? Here, see, there is some alpha here is positive but small. But small, what do you mean by this? As you increase the temperature, okay, resistance is increasing, but increase in resistance is very small. R2 minus R1 here alpha that is equal to R2 minus R1 by R1 into T2 minus T1. But here, okay, R2 is larger than R1, but it is not that large. Very. If, what is that? The change, increase in resistance is very small as you increase the temperature. Okay, therefore, they have small values of temperature coefficient of resistance, but it is positive. Okay. Why? Because the resistance does not change appreciably even for several degree rise in temperature. Several degree rise in temperature, the resistance will not change. It does not change. But for metals, it shows very immediately. As you increase the temperature resistance will, what is that? Immediately it will increase. It will show some change. Increase, but in alloys it increases, but the increase is very small, very small. That is why we are using these alloys for making resistance coils. Why resistance coils? For a given resistance R, as if you pass current through that, okay, the temperature definitely will increase now. Okay, heating effect of current you would have studied in your Joule's heating effect, you would have studied in your 10th standard. Here also we'll see in this chapter also. But what happens as you increase the temperature, as you are passing a current for a long time, the resistance, what will happen? The temperature may increase. As the temperature is increased, there is a possibility of change in the resistance in the metal. Okay, that is why. But if I want a resistance coil, I don't want Even if you pass the current, the resistance should not change. Even if you pass the current for a long time, the temperature will change, only temperature will increase, but I don't want the resistance to change. In that case, we prefer only, what is that, alloys, manganese constant tan, okay, or nichrome, whatever that. Usually it is manganese and constant tan. It is meant for, what is that, making resistance coils. Why? Because here its alpha is very less. It won't show appreciable change as you increase the change in the resistance as you increase the temperature. Are you following? So this is about at the same. See, now we are going to see temperature coefficient of resistivity. What is temperature coefficient of resistance? We have seen temperature coefficient of resistivity. Let me the same thing. Resistance we have seen. Temperature coefficient of resistivity. What is that? It is temperature coefficient of resistivity. This is also alpha only usually. Okay. So what is that? Alpha is nothing but what is that? Increase in resistivity. Increase in resistivity per original resistivity per degree rise of temperature. That's all. Are you following? So it is here, it is in terms of resistance, here in terms of resistivity. That's all. That is the only change. Okay. Therefore, what is that? Increase in resistivity per original resistivity per degree rise of temperature. This is what is called temperature coefficient of resistivity. Are you following? So now for the same thing, for metals it is positive, and for that is electrical resistivity increases with the increase of temperature. But for alloys, but for insulators and semiconductors, what is that? It is negative. As you increase the temperature, resistivity will decrease. Okay, therefore alpha is negative. And for alloys, as usual, it is very small. Okay, as your resistivity won't change that much with the increase of change of temperature, but it is positive. Okay, it is positive but very small. Hope you are following. It won't change. Resistivity will not change appreciably with temperature in the case of alloys. Okay, therefore, shall we go for plotting the graph here? Okay, with this, what is if I want for metal? For metals, okay, if I want to plot a graph, rho versus, okay, temperature, well, Kelvin, temperature Kelvin, and rho, what is the unit here is 10 power minus 8 ohm meter. 10 power minus 8 ohm meter, and the temperature here is Kelvin na, there was 0, 50, 100, 150, etc. And here it is 0 0.2, 0 0.4, okay, into 10 power minus 8 ohm meter. Okay, therefore if you say as you increase the temperature, what is that? The resistivity will increase, na? So it will be like that. It will be like that. Okay, even I can. Even better. Again, how nicely it increases like that. Okay, right. Next one is for constant tan. For I see. I can write. Okay, first I will for nichrome, because then after that I go nichrome. Nichrome is nothing but alloy, na? Alloy. So for that, if I draw this, see here, rho. Okay, rho is in micro ohm. Okay, centimeter. It is ohm meter, na? It is micro ohm centimeter. Ohm meter, it is micro ohm centimeter. Okay, so T is Kelvin. Okay, here you see here temperature is up to 200, there is no change. That is why this itself I am starting from 200, 400. uh, that means that after 200 there is no appreciable change in the resistivity in the case of what, alloy. Okay, therefore it is 1.00. Let me have, see, this is the difference, that is why I just want to 1.10, and here it is 1.12, 1.12 micro ohm centimeter rho. Okay, therefore how it will change, you see, up to, you can say it is 800. Okay, by 800 it changes from, either say, that's all. Okay, so from where, from 200, okay, from it is 0, okay, 0 Kelvin. From 0 to 800, if you increase the temperature, okay, how much it change? 1.10 to 1.12 micro ohm centimeter is only the change in the resistivity in the case of what? Alloys. The case of alloys. Are you following? And in the case of alloy, okay, this is alloy means what is a nichrome? Okay, but if I take constant tan, why I told you manganese and constant tan, no, they are meant for making a resistant coil. Why we prefer that one for manganese? If you see, um, for manganese or constant and whatever is said, okay, manganese or constant tan. Okay, what happens here, you see, this here itself the change in resistivity is very small only, up to 800 Kelvin. If you increase, that is a very small, it is thinking whether to change, increase or not, like that. But in the case of manganese or constant even, huh? That is the reason why we make resistant coils with manganese and constant tan. Okay, therefore hope you are following this. My handwriting here, it is very small now. It is manganese or constant tan. Okay, let me rub this properly. Manganese or constant tan. Okay, for that if you plot a graph, see, very nice, you see, nothing will change, no change at all, rho T. Even if you change up to 800 degrees Celsius, here at least there is small change is there, no, वो change भी नहीं है इसमें manganese con. That is why it is meant for making what is that, resistant coils. Okay, rather than nichrome or nichrome, whatever that, we use only manganese or constant for making coils, resistant coils, right? Okay, now the last one is how for semiconductors or insulators. Well, I think you know semiconductors and insulators, as you increase the temperature, there is an exponential decrease in the resistivity. There is an exponential decrease in the resistivity, is it? Therefore, insulators and semiconductors. Okay, therefore you can say for semiconductors, sudden increase, very, okay. For insulators, the temperature should be very high. Only then, what is that? The electron will think, what is that? You can say even for, I can say the exponential increase is only for semiconductors, I will say. Okay, semiconductors. Like what is it, germanium, silicon, okay, etc. Even carbon, okay. Therefore, the increase in temperature, therefore, what happens? Number density of electrons in the conduction band, okay, it will increase exponentially, okay, and therefore you can say what will happen. How to plot a graph here? Rho and this one, if you temperature, it is exponential decrease in the this one. Okay, therefore this, there is an exponential decrease in the resistivity, okay, in the case of what is that, a semiconductor.